Here we go. Okay. Trees, which is very exciting because it's the last chapter of the textbook, which means that we've just got some extra material that we're gonna just kind of put together. But we're in the home stretch. You're doing it. And the last topic is trees, which are just a special case of a graph. We talked about Euler circuits and Hamiltonian circuits or cycles on Friday, and kind of similar layout for trees. So a tree, just by definition, a tree is a graph that's connected and has no circuit. Okay? And this is the part that, oh, I don't remember having it in pink, but okay. So it has to be connected and it can't have a circuit. And if that's the case, then it's a tree. Okay, so that's fine. But the no circuit part is what we're gonna hinge a lot of it on, because you can look at a graph and you can see quickly if there is a circuit, and if there is, then it's not a tree. Okay, it's a graph, but not a tree. So in a tree, there's always exactly one path from each vertex in the graph to any other vertex. So only one path. Okay. Determine which of the given graphs are trees. Just gut reaction. A is not, because it's not connected, right? B looks good, right? There's no circuits, it's all connected, that's good. I'll write it down here, but I want to do the run through first, because we're going with our gut, right? Gut reaction, looks like a tree, talks like a tree, it is a tree, walks like a tree, quacks like a tree. D is not, because there are many circuits, right? Here, 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 all the way around, all on the quarters, right? There's lots and lots and lots of circuits, and that makes it not a tree. Also not a tree, because there's this one circuit, right? And so it's not a tree. A is not a tree because it's not connected. As a little fun fact, though, it is two trees, which we do call a forest. So that's cute. Two trees is called a forest. Or multiple trees is called a forest. That's not something that you have to know, but it is fun. B is a tree. C is a tree. D is not a tree, because there are many circuits. And E is not a tree, because there is one circuit. Only takes one. So a spanning tree is a tree that's created from another graph. So we could take any of these graphs up here that were not trees, right? And we can remove edges as long as we keep a path to each vertex, and the result is called a spanning tree, right? So the simplest version here, right, we have lots of options that we could remove and it would still be a tree, right? I could remove this little guy, right? Then I would have a path like this hitting every vertex, right? Or I could not do that one. I could do this one. Then I still have a tree. It's all connected. Or I could remove this one and I would still have a tree, right? So you only have to remove one of the edges and you would get a tree, which is a spanning tree because it didn't start out as a tree like this one. We're making it a tree. So for example, if I have some water source and the initial plan is to maybe lay sprinklers or something like that through a network, then if we want to form a spanning tree for this graph, we're going to eliminate edges that are not necessary, right? We just need a tree. And so there are many different options. And what I'm going to do, because I can and technology allows it, is I'm just going to copy the vertices and then I'm going to move them over. And I know that's cheeky. I know that. Whee! And I guess I could have copied the lines. Okay, move it back on. I'll copy everything. And then we'll remove them one by one. On yours, it might just be easier if you just put a little line through the ones that you want to cut, right? But you have a lot of different options, right? Focusing on this section over here, right? I could cut this line, right? Or I could cut this line, or I could cut this line or this line or this line. And depending on which ones I decide to cut, right, that's going to determine which ones I have to keep, because I still need access to all the vertices, right? So for example, if I cut this one, another option, so for cutting here, I could cut this one, or for symmetry, I like symmetry, I'm going to cut this one. Now all of a sudden I have access to all the vertices without any extra edges. And so we can do the same thing, and there are many, many different spanning trees that we could create, right? And so there's no wrong answer as long as you have no circuits anymore, right? And you've cut as much as you can. What's another thing? So focusing on this side over here, right? What could I do? I could, well, I don't think I need a connection here, 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 here. And with that, I would be done, because, right, now each of these, I have access to all the vertices, and then I would need this additional line over here. What's another thing you could have done? We could have, if I undo, it's another thing we could have done. We could have said, how about I cut this one and cut this one and cut this one? That's an option, right? There are many options. I like that one, because then I don't have 3 things flowing from the faucet. I only have 2. Yeah.
For this diagram, it looks pretty much similar with, like, when you go above, like, the one for example 1.
Yeah.
I just want to know, like, what's the difference? Because I mean, they seem pretty much similar too.
These ones?
Yeah, that one.
In the sense that you could, they are the same.
Oh, okay. I was gonna say,
yeah.
Like, would that be true too in the graph that we did?
Now it is.
Oh.
Once we've eliminated all the circuits or the cycles, then it's a tree, as long as it's still connected.
Oh.
Right. So if you did something like that, now it's 2 trees, a forest, if you will. And so you could do that, but it's no longer a tree, right? It's no longer one tree. So as long as it's all connected, then it's a tree. And because it didn't start out as a tree, it started out as this graph. That's why we call it a spanning tree, but it's nothing, it's not special. I'll just make a note of that here. Right, a spanning tree is when we start with non-tree and remove edges to create a tree. So just as a fact, as long as you're starting with a connected graph, so any connected graph will have a spanning tree, right? And in fact, it's going to have many, many different spanning trees, okay? And if the original graph has at least one circuit, then it will have several different spanning trees, right? So even from this itty bitty example that we had up here, we saw 3 different versions of this tree, right? I could cut this one, or I could cut this one, or I could cut this one, and they all create different trees. And we saw we had lots of options for cutting edges in this diagram here. And that's because we had those circuits to begin with. We're going to find 2 spanning trees. So we're going to take these graphs, eliminate the circuits, and create, and there, again, there are lots of different options because we have 1, 2, 3 obvious circuits in the first one. And so there's lots of different options. And then we have a ton of different circuits in the second one. But I'm going to use the same cheater method. And I know it's cheating. We copy, paste. It looks like a fox face. Cute. Okay. Again, lots of different options, but what's one that we could do? I could cut this one. I could cut this one. And for symmetry, because I like that, I could cut that one. Or what's the other option? I could cut this one. Weird. Cut this one. Now I'm just going rogue. Cut that one. A tree. In fact, a spanning tree. I'll trace this graph here. Boo, boo, boo. 1, 2, 3, 4, 5, 6, 7, 9, 10. I did not need to count them, I just did. Don't know why. Oh, that's weird. I think. Again, lots of options. For me, how about we just make a serpentine pattern? That's fun. We're going to hit every vertex, and they're all connected. That's an option. I guess we could do it the other way. All right, what's the other way? Boom, boom, boom. Boom, boom, boom. Fun. And easy. The no right answer bit is kind of, or no wrong answer bit is kind of nice, I guess. All right, now we're ready for minimum spanning trees. So the problem is that the length of each edge is often associated with a cost or a length, right? And so you want to minimize distances, you want to minimize the cost. And so we're going to have edge weights. Okay? In those cases, we're always interested in minimizing the cost or the distance, or usually they're kind of hand in hand. But if the edges of a graph have weight, then we refer to the graph as a weighted graph. That's pretty obvious, I think. A minimum spanning tree is a spanning tree for which the sum of the numbers associated with the edges is a minimum. Fair enough. And we're only going to introduce one method for finding a minimum spanning tree. Just one. And the method is this. Oh, I have to issue an erratum. We were debating whether it was a errata or erratum. Erratum is singular. The sorted edge method. The problem was that I was forcing us to start at the initial vertex, but it's actually open to any edge, which is going to be exactly the same as what we're about to say. So that's my erratum. Kruskal's algorithm says that to construct a minimum spanning tree for a weighted graph, we use the following procedure. You're going to select any edge with minimum weight. So you're going to include the smallest weighted edge in your tree. Okay? Then you're going to select the next edge with minimum weight among those not yet selected, obviously. And these don't need to be connected yet. They will connect eventually. Continue to choose edges of minimum weight for those not yet selected, but obviously be sure to not select any edge that forms a circuit because then it's not a tree, right? And then repeat until the tree connects all the vertices of the original graph, right? Which means it's connected. So find the minimum spanning tree for the weighted graph below. The weights represent the cost in hundreds of dollars. I'll do my sneaky copy thing again. But I also need the weights. Oops. I didn't like that. Oh, maybe I should do this the other way around. Why? Because I'm selecting the smallest edges. So I'll cut the edges. Reverse, reverse, undo, 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 Control Z, undo. I'll put them over here. I've got A, B, C, D, E, F, G. Looking at these weights, my first edge is AB with a weight of 1. Okay. So I'm going to add that to my tree. Now I'm going to just scour the graph for the next lowest weight, which is going to be 2. So now, whoops, which goes from B to G, which has a weight of 2. I've got 2 options for a weight of 3. I can't use this one because it would make a circuit, right? And so this one, I can't use this one because it would take me back to A, which I don't want, right? Then it's not a tree. And so that's the only caution that we have. So then we're going to include BC, which has a weight of 3. Again, there's a tie for the weight of 4. And so you're not going to use any edge that makes a circuit, right? But if I look at CD, it looks good. And if I look at G or FG, then it also looks good. So I'm going to include both of them. So I've got a weight of 4 and a weight of 4. And I want to make a note here that for these two, we're going to say unless one of these creates a circuit we include both in our tree. Okay. And then, so if we look, we see that E doesn't have a link yet. And so we're really hoping that there's a minimal weight that's going to attach E and make this a connected graph. Even if there isn't, there's no point, and you can't, because it's going to create a circuit unless you map to E. And so really what you're going to do at this point is you're going to go from E and pick the shortest edge, right? Or the lowest weight, which is 5. And now we can find the total cost. So now this is your minimum spanning tree. Which means that the minimum cost is 1 plus 3. I'm just going to read them kind of like this and then go back, which might be confusing, I guess. 1 plus 3 plus 4 plus 5 plus 2 plus 4. I get 19, which is in hundreds of dollars. So the minimum cost, oops, $1,900 or $1,900. It's pretty fun. There's a question very similar to this one on the final exam. That's nice. Can do it. I should. I shan't. Can't. But I should. I'll give you a practice final exam, which is almost as good. How about that? But just as a gauge of what you're expected to be able to do from this chapter, it's this. Okay, so let's practice that a little bit more. How about? So we've got a portion of the Santa Rosa Junior College campus, along with some walkways. I obviously stole this from somewhere else. And the lengths are shown in feet. Connecting the buildings is shown below. That's weird. Suppose the decision is made to connect each building with a brick walkway, and the only requirement is that there be one brick walkway connecting each of the buildings. So create a tree. We assume that the cost of installing a brick walkway is $100 per foot. And what's the minimum cost for this project? And so we want to find the minimum spanning tree using Kruskal's algorithm, because we don't have any other algorithms, and that's okay. You can look into other algorithms. Prim's algorithm is one that's in the textbook, and that's the only one I can remember off the top of my head. But I don't remember how it goes. So something about the bridges between, anyways, doesn't matter. We're only doing this one. Okay. So for this one, I'm not going to copy it out because we can select, right? We can look at the distances. Here, I'll zoom in. You can look at the distances and see that 5 looks good, 5 looks good. I don't have to make a choice here because they're both the smallest distances. So those are definitely in my tree. Then if I go up in value, my next value is 10, and there are 3 of them, right? But you would only include as many as you need to, right? In this case, all of them. because you want to, so you've connected Bailey to Busman to Shuha, and then you're connecting Beck to Lark to Baker, and then you're done. Often what we would do, if you have something like this, you would translate each of these just to a vertex, right? And just write them out without all this fluff. And by fluff, I mean buildings. But the idea is the same. Okay. So then the total distance is 5 plus 5 plus 10 plus 10 plus 10, which is 40 feet, which means that the total cost is 40 feet times $100 per foot, which means $4,000. Now I put it at the very end of the last page, but it might be worth noting that if you have n vertices, right? So if you have 1, 2, 3, 4, 5, 6 buildings, then your tree is going to have how many edges? It's going to have n minus 1 edges, right? And so you're going to have 1, 2, 3, 4, 5 edges, right? And so that's one way that you can check to make sure that your tree makes sense, right? Is that you're always going to be expecting n minus 1 edges. And I put that way down here at the bottom, but because I brought it up now, I guess I'll highlight it there. Because it's just a good check-in point, I think. Okay. What about something like this? A company is considering building a gas pipeline network to connect 7 wells, A, B, C, D, E, F, G, to a processing plant H. The possible routes and their costs are, and we've got all these routes, right? A to B costs 23, A to D costs 19, A to E costs 17, etc. What pipelines do you suggest be built, and what is the total cost? So I'll give you a little moment to try to map it out. And I guess my one thing would be to just put A, B, C, D, E, F, G, H in a circle and try to find your minimum spanning tree. It's a good exercise. I should say you don't have to graph them visually, but my brain doesn't work the other way. I can't look at those links and tell if they're all connected or not. looks something like that, maybe. Something. Not to scale, not to anything. What's the point of doing that? So that you can see if it's connected or not, right? Should I let you keep working on it? Yeah. Have fun. Minimum cost is going to be 115.
That's definitely like one.
The first few are fine, but there's kind of a sneak attack too at the end. Now, for me, I make use of this fact, right? So I have n vertices. In this case, I have 8 vertices, right? Including the plant H. And so I have, in this case, I have n equal to 8. So I need n minus 1, which is 7 edges, just as a check-in point in order for it to be connected. Okay. So like I said, the first few are fine. And what's nice is when you have the costs or the weights here, then it's easier to see what the smallest weight is, right? And so the first one that I'm going to add in is going to be this one here. So my first distance, or my first pipeline, is going to be from C to G. So the route that's definitely included, and its cost of 10. The next thing that I'm going to see if it works, and so far it will, is which one. I think there's an 11. Okay. And so up here, I'll just say 2, but I just want to make sure that from F to G, okay, that hasn't been done yet, so that's okay. So it is the second one. And as we go, I'll highlight these routes that we've taken. Already. Okay. What's the next shortest route? 14, right? So the third one, but before I commit, I'm just gonna make sure that it's gonna work. So D to E is down here, that's fine. And so I'm gonna include that in my route. D to E costs 14 to build, $14 to build a gas pipeline. No, the units are unknown. Millions, billions, I don't know. Thousands. That's cute. Okay. So we've done up to 14. I see a 15, just making sure that that is the next one. And so E to C looks good. Looks like I can include it, so I will. B to C had a length of 15 or cost of 15. And what's the next one? 17, I think. Just make sure. A to E is down here. Okay, that's allowed. So now A to E has a length of 17. This is where, at least when I look at this, I think, wow, only H is missing. But what's one thing that you could do? You could move this AED chunk because it's not actually connected to FGCB, right? So they're not connected yet. So you need to keep going until they're connected. Let's make a note about that. Notice, I'll call it AED, is not connected to FGCB, which means that, well, we're going to go by increasing order of weights here. AD, I can't have AD because it would make a circuit, and I don't want that, right? So I move on from 19 to 20. DF goes here, and it would connect it, so that's good. Here, I'll make a note, 6, but then I'm gonna draw a line through it and say that's not the 6 that I want. I want this as my 6. All right, just to indicate that, no, I created a circuit, so I move on. Okay. And the next one that I go for is DF. And DF connects the graph and at a cost of 20. Right, now I can go from E to C to G to F to D to E to A. Now it's connected, but now H is the only vertex that's missing. Okay. So finally, we need to connect to H. So to get to H, I only have 2 options of getting to H, regardless of whether they're the next lowest weight or these are my only 2 options to get to H. So you're going to choose the lowest one. Okay, the shortest distance is going to be this 28 from E to H. And let's list it the way it is here, EH, which has a distance of 28. Okay. What you would find if you worked through incrementally, so we stopped at 20, and if you go to, what's the next one, 23? Call this 7. A to B makes a circuit. Let me unravel this in my brain. Yeah, because I can go from A to B to C to G to F to D to E to A. That's a circuit, right? And so that one's not allowed. Moving on to the next one. So from 23 to 27, trying this one, right? You could just visualize it, or working through the list, that's fine too. That's all I'm doing. BF, well, if I do B to F, then I'm gonna get a circuit. I just need to see how. Yeah, I can go from B to F to D to E to A. Oops, sorry. B to F, there we go. B to F to G to C to B. There, that's my circuit. I just couldn't see it right away. So that's not it. Luckily, I'm on to EH, which I know is the one that I had to choose, right? Because I have to get to H. And then I'm done. Now the total cost here, once you add these up, is 115. So the minimum cost is 115 units, not committing to anything. We said, okay, we want to make sure that we have 7 edges and only 7 edges. Let's confirm. 1, 2, 3, 4, 5, 6, 7. Phew. And that's trees. And that's all I've got. Any questions though about trees? Let's start there. How about my erratum from chapter 9? They ended up being the same in this case, but here, this is, you're going to draw the graph showing the cities and identify. You don't define your starting, I guess that's still true. Okay, fine. You identify your starting vertex, where you want to start from, but then you choose the edge attached to that part is not true. Choose the edge that has the shortest distance. When I attached it to the starting vertex, that's what made it the nearest neighbor algorithm. Now, they're usually similar, so, but that's why. And that's the change that I would make. Choose the edge that has the shortest distance. And it would work out to be the same as the nearest neighbor in this case. So we're all free and clear. But in this example, right, from last day, just in general, you would choose the 51, right, which is attached to San Francisco, which is our starting vertex, right? And so 51 and then 96. I'm trying to remember, we're not doing trees anymore. Doing circuits. How come it's, yeah, we want to connect, yeah, circuits.
Just have to connect it once more to not make it trees.
Yeah, we have to make it our way back to the starting point. But how come this?
Go back up.
Travel along the edge to the next vertex. From that vertex, you choose the oh, I read up on this and now it's escaped me. Mm. Okay, fine. I'm not ready to issue my erratum. Because I feel like it should be 96 next. And then, but then it can't be 129. So maybe that's why we travel here. And then we're choosing between these two, shortest one, choosing between these two, but this one can't. So it has to be this one. And then we have to make our way back from Fresno to San Francisco. There, lackluster. I sort of convinced myself. Sort of. Needless to say, I won't make you do sorted edge. I like nearest neighbor. But I'll probably make you do the brute force method, because then you can establish which one is the minimum cost. You have to look at all of them. Ah, rude. Yeah. Okay. Okay. And with that, I release you. I have to make an assignment for trees, but I'll do that. Don't worry. And you had assignment questions,
I did, yeah.
but you're over it.
Yeah, it was, yeah, it's fine.
I'll stop the recording. How about that?